Hello, this is Dr. Behrang Askarian. I am a faculty in mechanical engineering at Washington State University. I am also a licensed professional engineer in the state of Washington, and my area of expertise is thermal fluids. This video is going to be about the psychrometric chart. So before you watch this video, you need to know like what the relative humidity is, what the humidity ratio is, wet bulb temperature, dry bulb temperature. When it comes to air and water in it, air H2O, that's the model we deal with. So you need to know how we model the air when it comes to HVAC, right? So this video shows how you can use psychrometric chart in solving an HVAC problem. This is a problem that includes dehumidification and cooling, and we're going to apply the first law of thermodynamics on it along with the psychrometric chart. After I show you that, I'm going to also show you how you can solve the same problem without using the psychrometric chart. You can solve it exactly and accurately using EES, engineering equation solver. So if I want to just wrap it up, this video will cover the psychrometric chart and how to use HVAC problems in EES when you don't have access to a psychrometric chart. In fact, in EES, you can solve the problems more accurately. So we're going to get all the same values that the psychrometric chart gives us in EES, and we're going to solve the problem. You'll see how that works. So before, as I said before, one more time, you need to know what relative humidity is. You need to know what humidity ratio, wet bulb temperature, dry bulb temperature, the total enthalpy of air H2O together. How do we define that? You need to know these things before watching this video. So it needs a little bit of background before studying the psychrometric chart. All right, so let's take a look at the problem. Then I'm going to introduce the psychrometric chart after discussing the problem, and we go from there. All right, here's the problem. This problem involves cooling and dehumidification. This problem is example 14-6 from chapter 14 of the 8th edition of Cengel's thermodynamics book. And I want you to go ahead and read it, then I'm going to explain. So let's read it for 1 minute. Okay, so when you look at this problem, we have a control volume that we need to consider. The dashed line that you can see here is the control volume, right? The blue dashed line is the control volume. And so what we have is at the inlet, this is the condition. We have the temperature of air. At the inlet, you have 30 degrees Celsius and 80% relative humidity. And you have the volume flow rate. You have the volume flow rate, okay, cool. And then what it says is that when it comes out of the other side, this is what I want. This is what I want. I want that to reduce that temperature from 30 degrees Celsius to 14 degrees Celsius. And I want it saturated. Why do I want it saturated? It's going to be saturated anyways, because this problem involves, condensation. So if you have condensate removal here, definitely you made phi 100%. Because phi is 100%, you have condensation here. So if it's inevitable, basically. So whenever you have like a problem like this, that condensation happens during the process, it's obvious that the phi that comes out the other side has to be 100%. You reach the saturation by reducing the temperature, basically. When we look at the psychrometric chart, it makes sense. We're gonna discuss it. The question is, how do we solve this problem? The first question is, okay, so what are we looking for? What we are looking for is the rate of heat transfer that you have these cooling coils, that what would be the rate of heat transfer that is removed from this in terms of watts or in terms of joules per minute or kilograms per minute or kilojoules per minute. Looks like by looking at this problem, the volumetric flow rate is given in terms of meters cubed per minute. So most probably, based on what I see here, Q dot is going to be found in terms of probably not watts. It's going to be in terms of maybe kilojoules per minute or joules per minute or something like that. Since the psychrometric chart gives the value of enthalpy in terms of kilojoules per kilogram of dry air, I'm sure that, eventually when you solve this problem, it would be convenient to find Q dot in terms of kilojoules per minute. That's one thing that we want. Also, it asks for the moisture remover from the air, which means this value, this m dot, that is the condensate removal, the m dot of condensate, which we can call m dot of, the vapor that is losing, but it becomes condensate. So I can show it by m dot of F, basically, because it becomes liquid, right? So I can show m dot F as the liquid. If you're familiar with thermodynamics, you know what I'm talking about. Why did I use subscript F? Because, in the steam tables, we have like the quality 0, we show everything by sub F, right? Like the H sub F is the enthalpy of saturated liquid, for example. That's why I'm doing this. Okay, so now we got the general picture of the problem. Next step is, before we go to the psychrometric chart, we have to apply the first law of thermodynamics and mass conservation for water and the air, dry air, basically, and the combination of air and water together. And let's see what we get out of this. Based on, if we have enough equations and enough unknowns, basically, we can solve this problem. We can calculate that m dot of, the condensate. So let's take a look at the problem. Let's write the equations. Let's see what we can do. Okay, so we're looking at the problem again. We want to apply the first law of thermodynamics and mass conservation. Let's see what we get. Okay, the first law of thermodynamics is going to give us Q dot, basically. This is what we are looking for. So let's apply the first law of thermodynamics for the system. What is our system, or our control volume in this case? The control volume is the dashed line that you can see here. This dashed line is, one more time, I can show it with red. This blue dashed line is the control volume. So I'm going to apply the first law of thermodynamics for this particular control volume. Let's see what we get. So the first law of thermodynamics is always Q dot net for this case, minus W dot net. If you're not familiar with the first law of thermodynamics, I have a video that goes over the first law of thermodynamics completely from the beginning to the end for open system, closed system, study all of them. And I'm going to share the link in the description so you can go back and watch that. Q dot net minus W dot net plus m dot times m dot of dry air for this case, h1 minus h2 equals 0. You might ask what happened to velocity and change in the kinetic energy, potential energy. They are absolutely negligible for a problem like this, so we don't have to worry about it. One thing that you need to know when it comes to HVAC problems, and that's the background knowledge that I asked at the beginning of the video, is that when it comes to air H2O together, we define the enthalpy of air in a very specific way. Like the enthalpy of air, this is the air H2O together. It's air and H2O together. We define it this way, that it becomes the enthalpy of dry air, the regular air, plus omega, the humidity ratio, times enthalpy of the water vapor, the vapor content of the air. That's how we define it. For example, for HA1, that would be omega 1 times HV1. And of course, so this is the background knowledge that you need to know. Why do we do this? Because when they define the enthalpy of air H2O like this, that if you multiply that value by the enthalpy by m dot of air, dry air, basically you get the correct enthalpy rate that comes into the system, all of it. So in one shot, if somehow I have access to that H1, which the psychrometric chart actually gives me that value, by multiplying by m dot of dry air, I get the total enthalpy rate at the inlet. What does it include? The total enthalpy rate at the inlet is the enthalpy rate of dry air plus the enthalpy rate of the water content. What do I mean by that? Okay, let's take a look at it. If this is what I mean, H dot at 1, the total H dot at 1, what is it? It's supposed to be the H dot of dry air at 1 plus H dot of water, the vapor at 1. Let's see if what I'm saying is correct. Okay, so I can rewrite this whole thing as m dot of dry air at 1 like this, times basically H of dry air at 1 plus m dot V, water content at 1, times the HV at 1. Okay, that's correct. And now if I go ahead and factor out basically m dot of dry air, let's see what happens. It becomes m dot of dry air at 1 times HA plus m dot of V1 over m dot of dry air at 1 times HV1, like this. Well, here's the thing. We already know that's the background knowledge that I asked for. M dot V1 over m dot of dry air at 1 is basically omega 1. So this is why basically that and the total enthalpy rate at the inlet becomes easily m dot of dry air at 1 times HA1 plus omega 1 times HV1, like this. And this term, we call this H1. And the psychrometric chart, what the psychrometric chart gives you, and what EES will give you for the air H2O model is in fact that value of H1, the total value of H1. So you don't have to worry about it. You can directly read that. If you have the m dot of dry air at 1, you can in fact easily basically calculate the total enthalpy rate. So this is what I wanted to show. And that's the same case for the outlet. For H dot, the capital H dot at 2, you have the same deal. So I don't need to re-explain this one more time, but that's the background knowledge that you need when you look at this problem. Okay, so let's go back to the first law of thermodynamics one more time. Okay, so one more time, I'm going to write the first law of thermodynamics, and now we, with open eyes, we know what's going on. Okay, one more time. Q dot net minus W dot net plus m dot of dry air, H1 minus H2 equals 0. How do I know that there's only one m dot of dry air? Because the process is steady state and we're not adding any air to the system. So m dot of dry air at the inlet and outlet are pretty much the same. That's, I know already that m dot of dry air at 1 is m dot of dry air at 2. It equals m dot of dry air total. However, the m dot of water changes because you have condensation here. You have condensate removal here. So m dot of water 1, in fact, is something, it's definitely different from m dot of water 2. And what's the reason? The reason is that if you want to write the mass conservation for water, this would be the mass conservation for water. We called this, if you remember, I called this m dot that is coming out at the beginning of the presentation. I called this m dot of F, if you remember. So this would be m dot of F plus m dot of V2. Water is V is vapor, right? That's it. Now, okay, this process doesn't involve any work, obviously, any power. It doesn't produce any power, and if there's any friction or head loss, whatever, we basically just ignore it. So what happens is this value, it becomes 0. It doesn't produce any power. It doesn't consume any power either. So the value of Q dot net that we are looking for in this case is basically just m dot of dry air times H2 minus H1. Now, because we're removing heat from this process, obviously, we will get the value of Q dot net because you're cooling it, basically. It's going to be less than 0. It's going to be a negative number, right? Okay, now let's see, in order to find Q dot net, what is our mission? I need to find 3 things, apparently. I need to know the value of m dot air. Okay, how do I find this? I'm going to show you how to find it. I need to find the value of H1, and I need to find the value of H2. Both of these values, I can find both of these guys from the psychrometric chart. Both of these guys, you can go to the psychrometric chart, right? Psychrometric chart, and find these values. Okay, what about m dot of dry air? M dot of dry air, if you notice in the problem, the value of the volume flow rate of air is given. Okay, that's interesting. If the value of volume flow rate of air is given, which is given at the inlet, if you divide that by the V of, so this is the specific volume of dry air, not dry air, a specific volume per kilogram of dry air. This is the interesting part. This V from the psychrometric chart at V1, like this is the specific volume. This is very interesting. Specific volume, but get this part, per kilogram of dry air. Because it's per kilogram of dry air, because this is how it's calculated on the psychrometric chart, and how EES will calculate it. I will show you how EES will do it. If you divide the total flow rate that is coming in per this value of a specific, this is a very specific volume. It is the specific volume of the air that has water in it. But the way they calculated it, they divided it by the M of dry air, right? So if you divide the total flow rate of air that is coming in at any, whatever it was, the number that we had was 10 meters cubed per minute. If you divide that by whatever that specific volume in the psychrometric chart, what you will get is the m dot of dry air, because that V on the psychrometric chart is calculated per unit, per kilogram of dry air. That's very interesting. So looks like we got everything. I can find H1 and H2 from the psychrometric chart, and I can find that V, specific volume per kilogram of dry air from there. And by dividing the flow rate, the volume flow rate by that specific volume, I can find m dot of dry air. And looks like I have my q.net. I am good to go. And that's what we're going to do. However, there is another problem. There's something else that this problem asked for, and that was the m dot of condensate. How much, condensate? How do we calculate this? Well, here's the interesting thing about how to calculate these values. That in general, there's an equation that I can derive it for you. This is the mass conservation for water, basically. Okay, so let's take a look at it. Let's see how I can manipulate this equation and find an equation that is good for m dot of water, the condensate. Okay, based on that equation, what I see here, again, based on this equation, just follow that equation. Based on that equation, what I have here is that value seems to be m dot of water vapor minus m dot of water vapor. It makes sense, right? That makes sense. But then now here's the question. What is, if I rewrite m dot of water vapor in terms of humidity ratio, then what do I have? This basically becomes m dot A times omega 1. And this becomes m dot A times omega 2, because m dot A, as I showed you before, doesn't change. So this can be written as m dot A times omega 1 minus omega 2. This is the equation I need. All right, here's another question. How do I find omega 1 and omega 2? They're either given or we have to find them somewhere. In this problem, what is given is not omega, if you remember. What is given is basically phi, relative humidity, not the humidity ratio. The relative humidity is given. Okay, so if relative humidity is given, I need to go to psychrometric chart and find these values omega 1 and omega 2 from the psychrometric chart. Then I should be good to go. I can actually solve the problem. So now we have a game plan, basically. And if you have looked at other videos of mine, this is what I do all the time. First, I don't deal with numbers. I just write a game plan. This is my game plan. Then I go to psychrometric chart or EES or something, and then I solve the problem. So this is our game plan. Let's take a look at our game plan. Our game plan is, okay, what do I have here? I have T1 apparently, right? T1 is given as 30 degrees Celsius. Phi1 is given as 80%. And V1, the V naught one, not V naught, V dot one, which is the volumetric flow rate, is given as 10 meters cubed per minute. Okay, cool. With these two values, and the total pressure is supposed to be 1 atmosphere. The psychrometric chart that I have is 1 atmosphere psychrometric chart. However, if you're solving this problem in Colorado or something and the atmospheric pressure is not 1 atmosphere, it's like at 90 kPa or whatever, then you need a different psychrometric chart. If you solve it with EES, you don't have any problems, because EES is, you can do any psychrometric chart in EES. You don't even need psychrometric chart. You just give it the pressure and the 2 other properties and you're good to go. Okay, so you go to psychrometric chart or EES, and what do you need to find? Looks like at the inlet, I need to find omega-1 because I needed it. Okay, what else do I need? I need to be V1, the specific volume I need, and I need to find H1. These three I need to find. At the outlet, what do I have? I have T2 equals 14 degrees Celsius, and I have Phi2 equals 100%. Okay, I go to psychrometric chart again, and what do I find there? I find omega-2 and I find H2. I don't need to find V2 because once I have m dot of dry air, I'm good to go. I don't need to do that again. So it looks like this is our game plan. So once I go to the psychrometric chart, I find these values, and then I come back and put it in the right equations. And what are our right equations? The game plan said Q dot net that I was looking for. If you write it one more time, Q dot net was m dot A, m dot of dry air, times H2 minus H1. M dot of the condensate was m dot of dry air times omega-1 minus omega-2. Okay, that's correct. And the question was, how do I calculate m dot of dry air? We said m dot of dry air you calculate as V dot at the inlet over V1, and you get all these values from psychometric. So the whole problem that at the beginning kind of looked, you know, for sort of some of you, but if you are not familiar with these HVAC problems, looked a little difficult. Just it is basically reduced to three equations. If you have these values from the psychrometric chart, problem is solved. So this is our game plan, and we're going to follow this game plan. Now, my next step is, okay, let's go to psychrometric chart and basically show you how we can find these values in the psychrometric chart. And then we're going to bring them back and put them in the equations, and we can solve the problem. So what I'm going to do is basically, I'm going to show you how to find the values, and we're going to write down these values. But I'm going to switch to EES directly because we want to solve the equations just to make this video shorter. So you get the best of both worlds, basically. Okay, let's go to psychrometric chart and see how psychrometric chart works. Okay, ladies and gentlemen, here's the psychrometric chart. This is the SI version of it. There's the English version of it. You can use that one too. So let's see how that works and how we can get the values that we are looking for. That's the most important thing, that we should be able to find the values that we are looking for, right? And when it comes to the psychrometric chart, there is something that is a little unusual about the psychrometric chart that, and we haven't seen before, is the way that the axes are put together, basically. So let's take a look at the axes. If you look at this, the x-axis here, this is your x-axis, which is the dry bulb temperature. Dry bulb temperature, if you know the you have the background I talked about at the beginning of the video, you know what I'm talking about. Dry bulb temperature is a regular temperature, the temperature of air. You say, I don't know, this temperature is like 40 degrees Celsius, air temperature, that's the same thing, right? Dry bulb temperature is the regular temperature, whatever we know. So it's going from left to right. That's increases in this direction, and the way it's put together, this line is the humidity ratio here. This line is the humidity ratio, and the x-axis was the dry bulb temperature. But they put it together this way. Okay, cool. And let's see how we can actually read it. Like, what are the units? X-axis for the SI version, these are the values. Like this is, for example, 50 degrees Celsius, or this is like 40 degrees Celsius or 30 degrees Celsius. So these, on the x-axis, the unit is Celsius, and these are like 0, 1 Celsius, 2 Celsius, 3 Celsius, 4, 5, whatever, and 10 Celsius here. So that's how you read the x-axis. Okay, so we got the x-axis temperature, we got it. What about the y-axis? The y-axis includes the humidity ratio, or what do we know, or what we know as omega, right? So I showed it in my equations also, omega. Okay, so how do I read omega? The first thing that you need to know about omega in the SI version of psychrometric chart is it is shown humidity ratio grams of moisture per kilograms of dry air. This part is very important. If you read this, you see it's grams of the moisture per kilograms of dry air, which means this unit is not exactly basic SI unit if you want to use it in equations, because it's grams of moisture per kilograms of dry air. What we have in our equations as omega is kilogram of moisture per kilogram of dry air. So what do you need to do? And we're going to show that in our equations. What you need to do is basically, when you read these values, for example, you see the 6, with the actual value of omega, you got to divide it by 1,000. So this is 6,000th, basically. Or this value of omega that is 10 here, that is 10,000ths. Basically, or 12,000th, right? So this is how you are gonna find omega. You get the value here, you divide it by 1,000, and then you get the actual value of omega that you can use in your equations. Okay, so we covered omega. There's a bunch of other things that you know, are interesting when it comes to the psychrometric chart, and let's go over those values. You know, here's the good thing about having it on screen. I can zoom on it and show you more things. So let's, for example, take a look at the humidity lines. So when you look at the psychrometric chart, this is basically, okay, this is the, let's look at it this way. All right, this is better. So this line here, if you take a look at this line here, this line is this line. You see this line? This line is phi equals 100%, which means the saturated air that you know, the water content of the air is maximum. You can't put more water than this, you know, into the air, right? So this is phi equals 100%, basically. These curves, these green curves that you see on the screen, these are basically phi. They are the relative humidity, basically. You have relative humidity of 10%, 20%, 30%, whatever, up to 100%. This line is 100%. Okay, cool. And all right, what else do I need to see here? I found you know, the humidity line, relative humidity lines. What about other things? There are other things such as the wet bulb temperature, these dashed lines that you can see here. So if I, for example, I you know, go here and zoom on it, you see these dashed lines that we have here. These dashed lines are basically, they are the wet bulb temperature. How do I read it? Well, if you pinpoint any point on the screen on this chart, you can read it. Let's give it a shot. For example, in the problem that we are dealing with, T1 is 30 Celsius and relative humidity is 80%. So let's see if I can pinpoint that particular you know, case of air on the screen and see all, I can find all these values. So let's do that. So 30 degrees Celsius. Okay, so this is 30 degrees Celsius. I'm going to draw a line and 80% relative humidity. So I get this line 30% and I just keep going up until this hits the relative humidity of 80%, which happens to be this line. Is that correct? That's the relative humidity of 80%. So this is the point I am interested in. Based on this point, I can read other things. For example, I can read the basically omega. Okay, how do I read omega? Omega, based on this, let's just do it carefully. Looks like omega is somewhere between 20 over 1,000 to 22 over 1,000. So it's probably like 21.5 over 1,000 or something like that. Looks like that's the value of omega. So if I divide 21.5-ish over 1,000, I get the value of omega. I got my omega. Okay, what else am I looking for? Let's say I'm looking for the volume, the specific volume per kilogram of dry air. Okay, that was another interesting thing what actually we needed to find. So I showed you these dotted lines where the wet bulb temperature, these dotted lines, these green straight lines, these guys, for example, these guys, I'm talking about these guys. Do you see these? These guys are basically the volume, the specific volume per unit of kilogram of dry air. That's very important. Okay, so if I am on that particular point, my question is that what would be the value of the specific volume? It would be somewhere between this one, this line, right? And basically this line, these two. Somewhere between these two. Let's read these values. One of them is apparently 0.88 meters cubed per kilogram of dry air, and the other one has to be 0.89. So it is pretty close to 0.89 where we are right now. This is where we are, right? So if I just, it's getting crowded here. This is where we are right now, which is closer to this guy, which is 0.89 meters cubed per kilogram of dry air. So I would probably pick a value very close to 0.89, maybe 0.88, I don't know, 7, maybe, I mean, roughly, that's how you read the psychrometric chart, basically. So that would be the value. Another thing that you can read from this chart is, let's do another thing. Let's just delete some of these. Another thing would be the value of enthalpy. We need the value of enthalpy. How do we read enthalpy? If you want to read enthalpy, basically, to read enthalpy, the way it works is to read enthalpy value, it's almost parallel. Enthalpy lines are almost parallel to the wet bulb temperatures, almost something like that. You see these solid black lines here? These are the enthalpy lines, and this is the value of enthalpy here. So if you need to actually read the enthalpy of this particular point that we are, you have to draw a line parallel to this line, basically, whatever you have here. It's going to fall somewhere between this black line and that black line. So if I just draw a parallel line, something that is parallel to those lines, I'm going to, get somewhere something like this. So this value seems to be about 85-ish, this value that you see here, between 80 and 90. What's the unit? Kilojoules per kilogram of dry air. That's good because I talked about it, that the enthalpy that psychrometric chart gives us is per kilogram of dry air. That's why it's good, because if I multiply it by m dot of dry air, I can get the total enthalpy rate of water and air together, so I'm good to go. And it looks like the value that I can read here is somewhere between 80 and 90, more, closer to 90, maybe about 86-ish or something like that, kilojoules per kilogram of dry air. And based on this method, you can read anything you want. So right now I covered omega. I covered the relative humidity, right, phi, wet bulb temperature, volume, specific volume per unit of kilogram of dry air, enthalpy per kilogram of dry air. I covered all of those except one thing that you might be interested in, and that's dew point. And we don't have dew point in this problem, but let's just, while we're at it, let's just cover it so you learn how to read dew point. If you want to find dew point on the psychrometric chart, this is what you do basically. So first, whatever that point is, in our case 1, we are here, right? This is case 1. So you pinpoint that location on the psychrometric chart. Okay, in this case, it's 30 degrees Celsius and the relative humidity of 80%. Okay, that's our point 1. What you do is you're going to draw a straight line. After you pinpoint that location, you draw a horizontal straight line so it hits the phi equals 100% line. Once it hits that point, then what you do, you draw just from that point, you draw a vertical straight line, completely vertical straight line, so it hits the x-axis where the temperature is. Whatever that temperature on the x-axis is, that's the dew point of this case 1. That's the dew point of this case that I'm showing by an arrow, basically. Okay, so for this particular case, what is the dew point? The dew point seems to be, let's take a look at it. Let's see, it seems to be, this is the dew point, somewhere between 25 and 30. It looks like it's 26 degrees Celsius. So for case 1, if temperature is 30 degrees Celsius and relative humidity is 80%, the dew point for 1 atmosphere, if the pressure is 1 atmosphere, the dew point seems to be 26 Celsius. That's the dew point. So we covered the psychrometric chart completely. right? So that's very interesting. And we can write down these values, basically the average values that we want. And so I'm going to, on one note, I'm going to show you the values I've got from the psychrometric chart. You can even, pause this part of the video and you go over it and, practice. So basically, if you want to practice here, and you can go to any, thermodynamics book, and all you need to know that this is where we are right now. So this is where we are. This is our point, basically, and you go from here. You pinpoint this location, and from here you find everything else using the psychrometric chart. Okay, so let's write down these values. And because we have our equations, now I'm going to switch to EES. I'm going to show you how you can find all these values directly from EES if you don't have access to psychrometric chart, or you have a psychrometric chart like this one that is at sea level, which means the pressure is 1 atmosphere, but you are solving the problem in Colorado, where the pressure is not 1 atmosphere. The pressure could be 87 kPa. So if it is 87 kPa, then what are you going to do? This psychrometric chart that I'm showing you does not work in that case. Then what do? Then EES can generate, first of all, EES can generate any psychrometric chart that you want. Also, you can find all these values at any pressure you want using EES if you write a solid code. And writing the code, solving this problem in EES only takes 10 minutes. And I'm going to write the code for you so you will see what I'm saying. All right, so let's write down these values and then go to EES, and then we're going to solve the whole problem in EES, and we're going to wrap it up. Okay, so you can pause this part of the video and double check these numbers because so I got the values from the psychrometric chart. Omega 1, this is the value I got, 0.0215-ish, doesn't have a unit. V1 that I needed because I need it for this particular equation, right? 0.885 meters cubed per kilogram of dry air. H1 about 86 kilojoules per kilogram of dry air, and omega 2 about 0.01, and H2 is about 39.3 kilojoules per kilogram of dry air. So these values I got. Now, because I have my equations, everything is good to go. These are my equations. I can show you, I can, put these values in the these equations, use a calculator and solve the problem. That's not a big deal. So you can do it yourself. You can sit down and do this yourself, and you just calculate the values and the problem is solved. However, I'm going to show you how we can solve this problem also in EES, so this video becomes more comprehensive, so it can answer all your questions basically when it comes to psychrometric chart and solving HVAC problems. So let's move on to EES. Again, if you don't know how to use EES, if you have never used EES, I have a video that I walk you through how to use EES in general. So I put the link in the description. You can actually look at that video first and then learn how to use EES if you have access to EES, and then come here and watch the rest of the video how I solve the problem using EES. So let's do it. Okay, so we are on EES right now, Engineering Equation Solver. If you have watched the video I posted, the introduction to EES, the first step when you you open EES is to check the units. You gotta have the right units, right? So we go to options basically, and I'm going to show you how we can solve that problem in 10 minutes. Basically, I'm going to write the whole code from beginning to end, and it's going to take 10 minutes. It's a very simple, the code basically. You go to unit system, right? Okay, so because I'm doing the psychrometric chart, I'm going to stay with Celsius. Kilojoules is fine. Kilopascal, I can do kilopascal. It's not a big problem. This unit system that I have is already okay. Let's put in the values that are important. First of all, pressure is supposed to be 1 atmosphere. So if you go back and watch that video I showed you, I went over some of these commands like convert or whatever. So I don't need to explain one more time. I'm going to convert basically atmosphere to kPa because my unit system is kilopascals right now. Okay, that's the first line of the, what else do I need to add? Basically I have T1 and T2, so I can have an array table, but because I have T1 and T2, I don't need to do array table. For array table, watch that video that I have on the Rankine cycle. I show you how to use array table basically. This one doesn't need array table because there are only 2 situations, or you know what, let's do array table. Array table works for this one too, because we have a lot of 1 and 2. I want to show you the dew point and things like that, so it's going to be helpful for you. So T1 is given, if you remember, as 30 degrees Celsius. Okay, so I got T1. What else do I have? I have Phi1. Phi1 basically is given at relative humidity as 80%, 0.8. And there was one more thing that was given, basically the volume rate. I don't need to put it in array table, so I'm going to call it V dot, basically V dot at 1. That's okay. It was 10 meters cubed per minute, basically. That was the unit. I don't have to convert it to the meters cubed per second, because you will see why for this particular problem. However, if you're interested in watts, then you'd better do that, because Q dot that you're going to calculate is going to be in terms of kilojoules per minute. Kilojoules per minute is not watts, right? It's not even kilowatts. So you have to, if you want to do watts or kilowatts, you got to convert this to, you know, meters cubed per second. So for consistency, for so far as this is good. What else was given? T2 was given. T2 was given as 14 degrees Celsius. Okay, that's cool. And Phi2 was given. Phi2 was given as 100% relative humidity. That was pretty much the whole thing. Pretty much that was the whole thing. So what's the next step? These are the given values. I can just you know, write the given values here. If you have looked at my other videos, the way that I write codes in EES, basically frequently I run them to, look for any unit problems to eliminate them before I move on to the next part of the code. So that's what I'm going to do here too. So I'm going to run this. Let's see what I get. Okay, this part is okay. Let's go to array table, and this is my array table. In the array table, everything looks good too. So phi doesn't have a unit. I don't have to worry about it. Now, I know I am on the right track. Make sure that, you save this code or something. So I'm going to also save it. Okay. Now, so I saved it, and let's do state 1. State 1, what do I have? I can save it one more time. State 1 is, I got to calculate a bunch of things. If you go back to OneNote, we were supposed to calculate omega, V1, and H1. Let's calculate them. Let's see how easy it is to calculate this in EES. Omega 1, okay. What did we find? If you go back to your notes, I hope you took notes. If you go back to your notes, omega 1 was 0.0215. That's what we got from the psychometric chart. Let's see what we get here. The function in EES that gives you the humidity ratio is called humidity ratio, or I can call it HUMRAT or something like that. Humidity ratio. Here's the deal. Here's the deal. When you want to do HVAC stuff and you want to get the values that the psychometric chart gives you, the substance that you use in EES is air H2O. That's the key thing here that you need to know. That's the substance. It's not air. It's not water. It's not steam. It's not any of that. It's air H2O. That's what you need for psychometric chart. Okay, cool. And you need 3 properties. One of those properties is always pressure. That's very important. That's why I told you, if you go to Colorado, the pressure changes, then you're going to change this pressure in these. And that gives you the correct psychometric chart or psychometric values for that particular pressure. The pressure that we have in this problem is 1 atmosphere. All right, P is P. What else is given? Temperature is supposed to be T1, right? Temperature is supposed to be T1. Okay, and T is T, the argument of the function. What about the relative humidity, phi? What do we use? It's for EES, the argument is R. You use R for relative humidity. R equals phi 1, okay? That's it, that's my function. I can calculate omega. Okay, remember that from psychometric chart, we got omega as 0.0215, something like that. Let's see what we get here. Let's run it. I'm gonna run this. I'm gonna save it first, and I'm gonna run this to see what I get. Okay, so it's in the array table. Look what I got. 0.02157. This is gonna be the exact value from EES. That's fantastic. I got this thing. I can get other things. I can get enthalpy. How do I find enthalpy? You use the enthalpy function in EES. That's fine. You just say enthalpy like this, and the rest, because it's state 1, everything is the same. I can just copy, Control C, and paste this whole thing here and get the enthalpy. And this enthalpy is going to be kilojoules per kilogram. We know it's kilojoules per kilogram of dry air. You don't need to type dry air for EES. Kilojoules per kilogram, we know it's dry air. So run it again. Now you have this unit problem. The reason is that in the array table, I did not define this. So let's just fix the unit here. This value is basically kilojoules per kilogram. Now I solved the unit problem. What did I get in EES from the psychrometric chart? From the psychrometric chart, the value that I read was 0.88 or something like that. Looks like EES is giving me a value, not point, I read the value of 86 kilojoules per kilogram. What I have here is gives me 85.29 kilojoules per kilogram, which is supposed to be more accurate. So just for you guys to remember, let me share that one more time. Take a look at this one more time. So the value of H that I got in EES was this guy, was 86 kilojoules per kilogram of dry air. And what did EES give me? EES gave me this value, 85.29. That's pretty good, and which is supposed to be more accurate. Okay, what else do I need to know here? I said I need three things for this state. I needed the volume, the specific volume per kilogram of dry air. Okay, that would be the volume function, which is a specific volume function needs. Again, I do the same thing. I can copy this whole thing because it's the same state and paste it, and I get this thing. And if I run it, I get the value of this, which is the unit is meters cubed per kilogram. The value I got is 0.8886 meters per kilogram. What did I get from the psychrometric chart? Let's go back and take a look at it one more time real quick. The value I got was this guy. One more time, it was this guy, 0.885. This is roughly what I read from the psychrometric chart. Okay, no problem. This works for me very, very well. This is supposed to be more accurate. So I don't need to go back and forth from now on. You know what the deal is. Now, I'm going to show you a couple of other things that this problem doesn't need, but if you're working with a psychrometric chart, you might have to use them. And that's the wet bulb temperature and the dew point. So there are two other things that we can add to this just for education so you know what's going on. All right, so the dew point, T dew point at 0.1, the function is just dew point, like this. And then you just use the rest of it for the argument of the function, exactly the same thing. And the wet bulb function is also wet bulb. So this is wet bulb TWB at 1 equals, basically just type wet bulb like this, wet bulb like this, and same thing, Control V. And now I have dew point and wet bulb in terms of Celsius. Let's see what they are. You remember that the dew point that I read for state 1 was 26 Celsius. Let's see what we got here. That's going to be interesting. So the wet bulb is 27 Celsius and dew point is 26 Celsius. So we were doing pretty good on the psychrometric chart. And the psychrometric chart is pretty powerful. So the wet bulb is 27 Celsius and the dew point is 26 Celsius. This is what I got on the psychrometric chart, if you remember. I got like 26. I got 26 almost exact. This is 26.17, you know, a little bit. So this is supposed to be more exact, to be honest with you. So that's the deal. Now I got everything. You can do exactly the same thing for state 2, right? For state 2, I can do the same thing. I can say omega 2 based on what I have is the humidity ratio, right? Humidity ratio of air, H2O, right? And P is just pressure, whatever pressure we have, and T is T2 that was given, T2, and basically relative humidity is phi2 that's what we have. Okay, I got omega 2. What did I read omega 2? Omega 2 from psychrometric chart, I got 0.01. Okay, let's run it. Let's see what we get. What we get here. The humidity, the omega 0.0099, which is pretty close to 0.01. That's great. That's fantastic. And I can do exactly the same thing for other cases. I can say, okay, H2, what is H2? Let's do H2. H2 is the enthalpy of, you just type it, enthalpy of, then I'm going to copy and paste this thing, Control C, Control C, Control V, like this. Then what else do I need? If you need V2, I don't need V2 in this for this problem. So if you remember, I needed only omega 2 and H2. And just to save time, I'm not going to calculate V2 and dew point and wet bulb for that case. You know how to do it. So It's good to know. Now let's move on to the solution of the problem. Solution of the problem is basically we just apply the equations that we had. We had only 3 equations. That's it. That's all I needed, 3 equations. What were those equations? Let's just look at those equations one more time. I had 3 equations. One equation for Q dot net. That was one equation for M dot A, and one equation for M dot of the condensate. That's it. I'm going to apply these 3 equations, problem solved. That's the end of the video. We're good to go. So let's do that. Okay, solution. So let's first calculate M dot A. We said M dot of dry air is calculated as the value of V dot at 1 over V1. That's how we calculate that one. That's the first equation. Second equation, Q dot net equals M dot of dry air, that value, times basically H2 minus H1, like this. That's what we got. And this Q dot is supposed to be negative, by the way. Let's see what happens. And M dot of condensation, is supposed to be M dot of dry air, like this, times basically omega 1 minus omega 2, like this. Okay. So let's take a look at our equations in the formatted equation like this. Let's see if it looks good. These equations look good to me. Beautiful. H2 minus H1. M dot F is M dot omega 1 minus omega 2. So I can basically go ahead and run it. So if I run this, I have these values. Now let's keep in mind, what are these values? Because I didn't change the volumetric flow rate from meters cubed per minute to meters cubed per second or anything, I didn't change the unit. This value is kilogram. That's interesting. Kilogram per minute, kilogram of dry air per minute. That's one thing you need to save. And this would be the kilogram of condensate water per minute also. That's important. And so I see another unit problem, which is Q dot net. Q dot net, as I told you before, because I didn't switch to meters cubed per second or anything, this value is not watts or kilowatts. This value is kilojoules per minute, right? So that's kilojoules per minute. Now I don't have any unit problems, and of course it turned out to be negative, which means our solution was correct. We extracted heat from the control volume, and everything looks good to go. You can now save it, and you have everything. The problem is pretty much solved. Now I want to show you one more thing before we go. So this is our solution basically. And one more thing I can show you is the solution, because this was example from the thermodynamics book, right? From Cengel's Thermodynamics, example 14-6, and the 8th edition thermodynamics. And let's just check our values. Let's see if we got the correct values, just like the values that the thermodynamics book has. So I'm going to switch to the thermodynamics book, and we're going to check those values. We got all values from EES, from Psychometric Chart. I'll show you the whole process. Let's see what we get. So this is the example. They use a psychrometric chart, hopefully, psychrometric chart. Look at these values. These values are pretty close to what we got. Like I got 86 from psychrometric chart. They are showing 85.4 somehow. Omega 1, pretty close. These values are all the values that I got. If you go back and check these values, I got these values. And the equations that I applied for you, so mass conservation and the first law of thermodynamics here, and eventually the values we were looking for. I got 11.25 kilograms per minute for M dot of dry air. I can check it one more time, but that's the value I got. For M dot of water, they call it M dot W, M dot water. I call it M dot F, if you remember in my code. Okay, that's fine. 0.131 kilograms per minute, and the value of Q dot, they got 511 kilojoules per minute. Remember these numbers, write them down. We want to check the EES value. So go ahead and check the EES values. Let's go to EES and check those values. Let's see what we got. So the values that we got in EES, basically, these are the values that we got in EES. I got, it was about, I guess, 511 or whatever it was. Now I have negative 518 because my code shows Q is going out of the system. Yeah, so it's pretty close. Why do we have this difference of, from 511 to 518? About like 7 kilojoules per minute, because basically I used more accurate values in EES. That's why. The book used the psychrometric chart. And look at the values of m dot of dry air, same value, 11.25 kilograms per minute, and pretty close value to m dot of water from the solution in the book. So everything basically checks out. So thank you very much. I appreciate it. If you have any questions about this, you can go back and watch the video, pause it, you do whatever works for you. Make sure you subscribe to this channel as I try to upload videos in the area of thermodynamics, heat transfer, thermal system design, fluid mechanics, things like that. I put the link to the descriptions I put the link in the description to how to use EES and what was the other one? To the First Law of Thermodynamics, the lecture. Thank you very much. Have a great day. Thank you for watching.